Romain Slootmaekers, and he was here, and we work at Incubate. And I'm going to talk about just why and how we bootstrap functional programming at the company. Nicolas touched the question yesterday about who we are, because the answer is not that trivial. It's actually, well, the official story is that Incubate is a technology incubator and that offers services for lots of small companies that are all involved in cloud computing. Well, every aspect of data centers and cloud computing. So we have a company that does buildings. It just makes building for data center. There's a company that does rack monitoring hardware to see if the power is still on, things like that. There are also companies that just provide a software stack to do billing and metering of people that use cloud computing. So we're all over there, and what Incubate does is we offer services to all these companies. For example, legal services or accountancy, but also technology and even sales offices. For instance, for a small company it's difficult to have a sales office in the States if you're based in Belgium. So the other part is that we try to be a spin-off generator, so that as soon as we discover or have a new piece of technology that fits the puzzle, we try to spin it off in a different company. So some of these companies that we built were acquired by larger companies to fit their puzzle. And some of the companies that are currently part of the symbiote, Amplidata, which was dispersed storage, Reactivity, those are the guys that do the level hardware things. Desktech, that's the one that builds buildings. And Cloud Founders, they offer sort of private cloud to level 2, not so little companies. To tell you a bit about how and why we bootstrap functional programming, I need to explain a bit about the problem we were solving. And that is, well, in a few years ago, in 2008, we were building what the market later was going to call a dispersed storage system. We were clueless back then that it would be called like this, so it had another name. But the thing is, it's a storage system for consolidated data, for big data, everything from, let's say, 32 megabytes to 32 terabytes. If it's that size and if it doesn't change anymore, the system can store it. And the concept is actually quite simple, because mathematics helps a lot. The thing is, it's based on the solvability probability of large pseudo-random binary linear systems. But it's quite interesting, but not for you. But the management summary, or the summary for the functional programmer, is that basically, if you have a system of linear equations that's solvable, you can, and the solution is your data, you can just replace the data with the system and its right-hand side and store that. And that gives you a lot of flexibility. For example, in the data itself, things are ordered, while in the system of equations, equations have no order. So if you store the rows like that, then you can store any row anywhere. So you have lots of flexibility, and the only thing you need to do to get the data back is solve the system. It is really interesting, and mathematically it's really sexy, but it's for something else. Anyway, you have a system where you have a client trying to store a big chunk of data, and it streams it towards this thing that does encoding, so it builds a system. And then you have something that says, yeah, I want to be able to lose 6 disks or 7 disks or whatever, and it still needs to be available. So the policy determines how many disks you need to use, how many equations you need to generate, and then you have something like provisioning says, okay, which disks? specifically which is that disk. And so after you've picked the disks, then you send these equations to the storage nodes, they store it, and then of course you have to record a bit of metadata to be able to find your equations again. So that's really the simple view of the system. Now, we were in pain, real pain, because the mathematics work out really well, it's robust, it works, but our implementation was not so unbreakable. Problem was basically resource management for one. Things like memory. If you do this, the first version was in C++, big important thing to say. And if you have to do your own memory management, you tend to keep things simple. So you keep it symmetrical, basically allocate something, do something with it, and then free it again. But somehow, somewhere, sometimes, or a lot of times, you want it to be something different. Like you allocate it here, do stuff there, and then somewhere all over the other side of the code base, you want to free it. And that's really difficult. Another thing is that the data gets sent over sockets. And sockets are really, really wild, annoying beasts. Lots of things can happen there. But the most important thing is that as soon as you want to do something, it tends to block, or you have to do some asynchronous solution to work with it, and it's quite tedious. And for moving out big data, it seemed to us that it was a good idea to combine sockets and threads. So you have a thread, you have a socket, you attach a thread to it, and let it pump out the data. But problem is that threads are also really wild beasts, and combination is, well, basically try to think of a scenario where you need to kill a thread and clean up its mess. It's really annoying. And the irony is that once you build an equation, it doesn't change anymore, it just needs to be transported. And so conceptually, it never changes, but somehow, somewhere, our product was able to corrupt these things, sometimes just because of silly software bugs. And that was also pain. And the last part is basically this cost of object orientation that's not too well known, but what happens is that if you use object orientation, your memory model is not very local. Basically, you scatter your allocations all over the place because of the objects, and then you lose locality, and then computers are not so fast anymore, and so your performance. So our system was not very performant while we were using C++. All these problems said, like, okay, your system is not good. And we were all basically firefighting and trying to fix all the problems, and we really couldn't. But we were also in luck. If you look at the core code base, you see that the Pareto principle applies. 60% of what we do is actually I/O, push things around. And 30% of the time is taken in, let's say, encoding and decoding systems. So large systems take some time. Now, the lines of code allocated to all these things are a totally different picture. Let's say like, really small part is I/O, and the codec is all something like 1,000 lines of code. And then everything else, 90% of the code is just for 10% of the time. And that's actually a good thing, because it means that most of the code is not really performance critical. It's really good. And we were planning to do a version 2.0, but we're still fixing all the problems with the version 1.6, and the 2.0 version had to have lots of new functionality. And I said, like, okay, now is the time is right, we're in pain, I will keep them when they're down. And I placed that. I said, like, look, I took a little component and said, I will rewrite this in camel, and it will be functionally identical, same performance, and it will just take 2 days to do this. And 1.5 days later, drop-in replacement was demoed, and we were allowed to investigate something else. And some of you might not really believe this, but it is actually quite simple to do these kind of things, because the component was really simple. It's actually just a socket server that talks to the protocol, takes some data, pushes it down to disk. Not a lot, not complicated. And I had perfect specs. The existing code is perfect. And there was also a test suite that really would allow me to see whenever I made a mistake. And performance of the thing is actually, it's system calls, and it's the performance of your network, performance of your disk, but there's not a lot of complex things going on. And OCaml has object orientation, which basically allowed me to not think and just copy the existing architecture of the thing. And it's good for these kind of things. For building your own thing from scratch, it's not so good, but for these things, it fits. And good thing was that people were quite impressed with the fact that you could just take out components, replace it with something else. It could be in a different programming language, and it would actually work. And that was a good thing. So we investigated something else, and we were not convinced that OCaml was the right solution. We were convinced that OCaml was a less sucky solution than C++, but maybe there were better solutions. And we also were planning the next version of the product. So we had already lots of ideas on how to do it better. And we would do more parallel computing and concurrency in the I/O. And so the performance would go from 30% of the time to something like 6% of the time. That was our estimation. We would recycle the codec because it seemed good. And we do everything else of the code in comfort. So that would cost some performance, but we would be comfortable and we would be assured that it would be correct. And maybe we would do something about the metadata I/O, which was a dirty little corner of the whole application. And so the estimates were that from 100% of the time it would be faster, and the size of the code base would be smaller. We played around a bit with programming languages, and in the end we decided on OCaml. And it was okay. But what happened? So we decided on functional programming, picked OCaml, we built it using lightweight threads, and we were blinded by success. Like, okay, this stuff works, and we can move forward. So we did lots of things that were way more complex than we anticipated. Then performance was really good, so the codec became a bottleneck, so we had to rewrite it again because it was the next bottleneck. And we did something about the metadata as well. That this became the distributed, consistent key value store that's Arakoon, which is also written in OCaml. And we suffered feature creep. So we had lots of new ideas and new features and things like that, and it fit not. So the performance went really up. From 100% time, we just were more than 2 times faster. But the size was the same, about the same. And if you take a look at the split up, it's like 90% is OCaml, 9% is C, 1% is assembly language. And that thing feels fine. So were we happy? Back then, in 2010, yes, we were happy. Type inference is a really powerful tool. It says a lot of things. Basically, it's like this neo-Nazi that beats you and says like, no, this is wrong, this is wrong, this is wrong. And at first, it's frightening, but you tend to love it in the end. The compiler is super fast. It builds your whole code base in seconds, while we were suffering with boost and It was hours. And the code that it produces actually, it's not super fast, but it's more than fast enough. And the foreign function interface is really nice. So if in the end you have something that's not so fast and you need to go down, you can do that, and quite comfortably. And refactoring was actually one of my fears, because when we were looking at OCaml, we said, oh, there are no refactoring tools, while in the Java world, if you want to do refactoring, you just grab the class and move it about, or grab the method in your IDE, move it about, and it has been refactored. But as it turned out, refactoring is actually sort of built into the language because of the type system. And so we had comfort in that as well. But we were not so happy. One of the problems was it's a small language. Well, it's not a small language, but there are not a lot of people working in there, so there's not a lot of things available. Like tools, what tools? Heap profiler? No. We also had a bit of problems with 32-bit, 64-bit things, but basically 32-bit processors are a thing of the past, so I'm not going to talk about that. And we had some problems with multi-core. The OCaml garbage collector is a single-core thing, and they have been explained. Well, they explained to us that the type of the strategy for leveraging multi-cores that we wanted to use is not a good strategy, but we had all these cores and we wanted to use it. So we had to do an ad hoc solution and do it anyway. And it would have been nice if there was language support for this. And OCaml has a learning curve. It's not to be underestimated. And there's no IDEs. Maybe we should do what James Street does and just force everybody to use Emacs, but developers are more stubborn than triggers, I think.
Yeah, we have plenty of the answers.
Yeah. And object orientation, as it turns out, is some of the features of OCaml that we use less and less and less. What happens is that functional programming has a tendency to push out resources out of the objects, and then the objects become empty shells with not a lot of state anymore, and then you can just basically throw them away and use modules and values. And one of the other things, and it was also addressed that here, that there's no tools to talk about architecture. Let's say more than code that spans more than one module. If you have like 50,000 lines of code, you want to be able to talk about the architectural things, about how things work. And there's no notation, there's no diagram things. In the object-oriented world, you have UML, which is tends to be overused, but it's nice to be able to explain how the structure of your code is. And there's nothing there. So, few years down the road, are we still happy? Yes, functional programming strategy works. In the end, it fits our problem. With distributed systems, we don't do complex things, and the complex things we do, like the generation and the solving of the systems, are not done in OCaml, because we think it's not the right domain. So, but in general, it works. But we're not so happy with the way the language has been evolving, or the runtime system and the library. Well, the library does not evolve, and so everybody tends to write his own, and then you have libraries where they have been abandoned. Libraries that are kitchen sinks. So it's a bit difficult. And we have also made a lot of mistakes ourselves. For example, we underestimated the learning curve. And so even if you understand how it works, you need a lot of practice to be good at OCaml. And for instance, if you have architects managing the larger picture, if they don't write a lot of code, they tend to become not so good as the developers that they're supposed to be coaching. And that creates friction. So, for example, one of the anecdotes is that there was this developer who says, like, no, I'm not going to write a unit test for this. It's obviously correct. And because it's a fault. And discussion. In summary, doing everything in one programming language is actually, in my opinion, silly, really silly. But to convince other people of that, you need to have some guerrilla tactics. For example, wait until they are in pain and then do something that disrupts it. It has been said before today several times, like functional programming and distributed systems, they match. It's a good match. And yes, if you do that, things will turn out quite well. You'll still be in pain, but you will have different kinds of pain. And as a closing remark to all the competitors out there that build storage systems, you should really, really do everything in C++.